Now let's look at coefficient of mutual induction. So basically, how effective is our setup so that the induction takes place. So any change in the first coil, how effectively is seen in the second coil. To give it a mathematical dimension to this, we use coefficient of mutual induction. So the basic idea here is coefficient of mutual induction between two coils measures how effectively a change in the current in one coil induces a EMF in the other coil. Let's look at the math. So again, here too, we know that the flux is linked to the current, and in this case will be equal to Mi, where M is your mutual inductance. Now, so when we relate this to our change in primary coil sets up induced EMF in the second coil. As per Faraday's law, the induced EMF is equal to the negative of the time rate of change of magnetic flux, that is this, right? And when we substitute it, we'll end up with M di by dt. Again, this is just an introduction. There's one more layer of math that we'll be learning. So this is by substituting Mi over here. So this is from say 1. Now, to define this, how is that we're going to define this? Yes, taking the same expression. So this is the one which we had to figure out. This is the one which we can vary. And so we'll vary that. For di by dt is equal to 1 ampere per second. We have the induced EMF is equal to the mutual inductance. So mutual inductance of two coil is numerically equal to the magnetic flux linked with one coil when a unit current passes through the other coil. Okay, let me rephrase this. 2 is right actually, but as per this derivation, this would be your definition. The mutual inductance of two coil is numerically equal to the induced EMF in the second coil when the current in the primary coil changes by unit, or the rate of change of current in the primary coil is unit. Okay, you can define it both the ways. The initial definition was based on this formula actually, guys. Right? So that 2 is right, but as per this set of steps, that should be the definition.